A wonderful day to everyone. Today we are continuing our lecture videos on Math 40. Our lecture for today is on orthonormal bases and the Gram-Schmidt process. Let's start with the idea or the concept of the inner product. What is an inner product? An inner product is defined on a vector space V, and it is a function denoted by left angle, right angle, from V cross V to the set of real numbers R. Specifically, if we have two vectors U and V on the vector space V, then the inner product of U and V is some real value R. And we get an inner product if the following conditions are satisfied. So firstly, the inner product of a vector with itself is greater than or equal to the zero value, or the inner product of a vector with itself is non-negative. And we get equality, so meaning equal zero, if and only if U is the zero vector. Otherwise, if U is not equal to the zero vector, then the inner product is strictly greater than zero. And for that, this is called the positivity axiom. Secondly, the inner product of U with V equals the inner product of V with U. So we call this the symmetry axiom, and it behaves very similar to the commutativity principle. The third condition is the inner product of the sum U plus V with W is equal to the sum of the inner product of U with W and the inner product of V with W. This is the additivity axiom, and it looks similar to the distributivity axiom. Finally, if we have a scalar value or a real value K, then the inner product of K times U with V is equal to K times the inner product of U with V. So this is called the homogeneity axiom. And it appears that you can take out or factor the K out of the inner product and multiply the inner product by K. Now, a vector space that is imbued with the inner product is called an inner product space. So for example, when we were studying the space of vectors in Rn, we were introduced to the dot product. If you recall, if we have two vectors U and V with these components in Rn, then the dot product denoted by U dot V is equal to the sum of the product of corresponding terms in U and V. And that is what we have there, U1, V1, plus U2, V2, plus and so on, plus UN, Vn. Now, is the dot product an inner product? Yes, if it satisfies the four conditions. So let us check. Let's consider this notation here to be the dot product. So the dot product of U with U, so you just multiply the corresponding components of U. So U1 times U1, you get the square, and so on, UN times UN, you get the square. And so we are squaring the components and we get the sum. And if U is not equal to the zero vector, then all the terms there do not sum to zero. In fact, the sum will be strictly greater than zero because at least one component of U is not equal to zero. So at least one squared term is a positive value. And also, if we take U to be zero, then since all components of U will be zeros, then the squares of those components will also be zeros. And when you add all of them, you just get the zero vector or the zero value. So the zero dot product happens when U is equal to the zero vector only. So this satisfies the positivity axiom. Secondly, if you get the dot product of U and V, so that is written as U1, V1 plus and so on, U and Vn. But take note that per term, we just multiply two numbers. And multiplication of real numbers is commutative. So yung U1 times V1, pwede mo siyang isulat as V1 times U1. Okay? And so on, Vn times Un. But by definition of the dot product, this is just the dot product of V and U. So we can see that the dot product of U and V equals the dot product of V and U. And this satisfies the symmetry axiom. Thirdly, if I have the sum U plus V and take the dot product with W, so by property of the dot product, we can distribute the W to the sum, and we get U dot W plus V dot W. But U dot W, as our notation was defined earlier, is just this notation over here. And so the dot product of U plus V with W equals the sum of the dot product of U with W and the dot product of V with W. And this satisfies the additivity axiom. Finally, if I have a real value K, the dot product of KU with V is the same as K times the dot product of U with V. This is a property of the dot product. And so by our notation, this is just K, the dot product of U and V. And this satisfies the homogeneity condition. So since all conditions for an inner product is satisfied by the dot product, we conclude that the dot product in Rn is an inner product. Now, from henceforth, we can say that Rn together with the dot product is an inner product space. In fact, whenever we mention Rn as an inner product space, we consider the dot product as its inner product, unless we explicitly specify another inner product. Now, to give an example of another inner product, let us first define a very important concept in matrix analysis, and that is the trace of a matrix. Given a square matrix A, which is n by n, the trace of a matrix, we denote that by TR of A, is given by the summation of A sub II. So what would be A sub II? In your matrix, A sub II denote the diagonal entries. So we are taking the sum of the diagonal entries, and the sum is equal to the trace. For example, consider this matrix A. Okay? So what is the trace of the matrix A? So the entries of A may look complicated. May mga E squared pa tayo, may mga pi, may decimals, may fractions. But we are not really concerned about that because the trace is just the sum of the diagonal entries. So you just add the diagonal entries and you get 8. So the trace is equal to 8. That is the trace of A. So some properties of the trace are as follows. Firstly, the trace of K times A equals K times the trace of A. So this tells us that in a way we can factor K. And that's true because the diagonal entries of K times A are all multiplied by K. So when you add them, a common factor is K. So you can just factor K and you just add the entries A sub II. And so we have this factored K here. Now the second property of a trace is the trace of a sum is equal to the sum of the traces. And the third property is the trace of A times B equals the trace of B times A. Now take note that matrix multiplication is not commutative. So A times B is not automatically B times A. However, the traces will be equal. And then next is the trace of a transpose equals the trace of the original matrix because the diagonal entries do not change position when you're taking the transpose. And lastly, the trace of A transpose A is non-negative. And this is only equal to 0 if and only if A is the zero matrix. So with this, we want to define an inner product. So consider n by n or square matrices U and V. So let's define this product. So firstly, let's just call it a product. Then if it satisfies the inner product, then we call it an inner product. So consider the product UV defined as the trace of U transpose V. So is this an inner product? So by property of the trace, the product of U with U is the trace of U transpose U. And we have shown by the last property earlier that the trace of U transpose U is non-negative, and it is only equal to 0 if U is the zero matrix. And that is the positivity axiom for an inner product. How about this one? So the product U times V, U and V is the transpose of U, is the trace of U transpose V. Now take note that the trace of a matrix equals the trace of its transpose. So if we take the transpose, okay, and remember when you take the transpose of a product, then you get the product of transposes, but the positions of the transpose get switched. So yung U transpose V, pag kinuha mo yung transpose niyan, magiging V transpose, tapos U transpose transpose. Okay, but U transpose transpose is just U. So by our definition of the product, this is the same as the product VU. And so because of the equality here, we see that the product UV equals the product VU, and that satisfies our symmetry axiom. How about the third condition? So if we get the product U plus V with W, that is the trace of U plus V transpose with W. Now operating inside ito, the transpose of a sum is the sum of transposes, okay? And then matrix multiplication is distributive, but we are particular on the placing of the matrices. So kapag nag-multiply tayo on the right, then it gets multiplied on the right. So this is the same as U transpose W plus V transpose W. Now, the property of a trace is the trace of a sum equals the sum of traces. And this defines our product. The first term here is just U, the product UW, and this is the product VW, and we just add them, and this shows, by transitivity, this shows the additivity axiom. And lastly, if we have a scalar K, and we get the product KU times V, so that is the transpose, the trace of KU transpose times V, and the K doesn't really get affected when you get the transpose. You can factor the K, in fact. And so you just get U transpose times V, and by property of the trace, the K can come out. So the trace of K times the product equals K times the trace of the product. And the definition is this is K times the product UV. And this satisfies the homogeneity condition for an inner product. Therefore, we conclude that the trace is an inner product. In fact, it is called the Frobenius inner product. And this inner product acts on matrices. Okay, so let's have some additional definitions. So suppose that we have a vector space with inner product, and let U and V be elements of the vector space V. We say that U is orthogonal to V, or the symbol is U perp V. Ang alam natin sa symbol na yan, perpendicular sa geometry. Pero sa vectors, the proper term is orthogonal. U is orthogonal to V whenever the inner product UV is 0. Okay? Secondly, we define the norm. Some use the term magnitude, pero the proper term is the norm. The norm of V is defined as the square root of the inner product of V with itself. And we use the symbol, these 2 bars here and 2 bars on the end. We say that V is a unit vector if the norm of V is 1. And lastly, the distance between 2 vectors U and V is defined to be the norm of U minus V. Okay, take note, yung distance na to may not be the typical distance that we know. For example, consider this vector space of 2 by 2 matrices with real entries. And then let's equip this with the Frobenius inner product. So let's say we have these 2 vectors, U and V. So the product UV is equal to the trace of U transpose V. That's how we defined the Frobenius inner product. So computing that, so the transpose of U is given by this matrix here. And then you just perform the multiplication inside. And actually, we don't need the off diagonals because the trace only adds the diagonal entries. And so the trace here is 8 plus -8 equals 0. So ano yung conclusion natin? What can we say about the matrices U and V? If their inner product is 0, then they are orthogonal to one another. Okay, that's something. And that's something new. Kasi pwede palang orthogonal yung matrices. Diba? At pwede lang yon kasi we defined the orthogonality in terms of the inner product. Second thing is, what is the norm of the matrix V? Kapag vectors yan, ang iisipin natin, it's the length of the vector or the magnitude. Pero matrix to eh. So hindi siya the usual length that we know. But we can define its norm. And the norm is just given by the square root of the trace of V transpose with itself. So ito yung transpose ng V, ito yung V. You get the product, and we are only concerned with the trace, and the trace there is 14. So the norm of V is the square root of 14. What is the distance between U and V? What is the distance between 2 matrices? Okay, so paano yon? So we get the norm of U minus V. So that is the square root of the trace of U minus V transpose times U minus V. So ito yung U minus V. So ginawa na natin. And then ito pala yung U minus V. Yung nasa left yung transpose. No? And then you just get the product. And the diagonal entries will be 4 and 40. We add to get the trace. And you get the square root of 44. And that is 2 square root of 11. So the distance between the 2 matrices is 2 square root of 11. Now, some identities and inequalities are defined or theorized for the norm. So we call these properties of norms. So firstly, the norm of V is equal to 0, the 0 number, if and only if V is the 0 vector. So if you get a norm which is equal to 0 and V is not the 0 vector, then something is wrong. Definitely wrong. Okay? Secondly, the norm of a scalar C times V is equal to the absolute value of the scalar C times the norm of V. Thirdly, if U is orthogonal to V, then the square of the norm of U plus V equals the square of the norm of U plus the square of the norm of V. Now it looks like you have here 3 squares. So para bang if you look at this as C squared, this is A squared plus B squared. So ano nga yung theorem na C squared equals A squared plus B squared? Ang tawag natin doon, Pythagorean theorem. And that is in fact the same term that we use. This is the Pythagorean identity. Take note, this only happens when u is perpendicular to v. Otherwise, if u is not perpendicular to v, we have the more general case here. So the square of the norm of u plus v plus the square of the norm of u minus v equals 2 times the sum of the squares of the norms of u and v. We call this the parallelogram equality. Okay? And number 5, the absolute value of the inner product uv. So yung nasa left na ito, real value yan, no? Absolute value, is less than or equal to the product of the norms of u and v. Okay? We call this the Cauchy-Schwarz inequality. Okay? The Cauchy-Schwarz inequality. A very popular inequality. You will encounter this time and again. And lastly is the inner product, the norm of u plus v is less than or equal to the norm of u plus the norm of v. If you look at u here as a vector, and then v is another vector, what is u plus v? It is the vector in a parallelogram, which is a diagonal. No? So para bang it's, you go to the vector u plus the vector v, and you get u plus v. Geometrically, you form a triangle. And what this is saying is like the two sides of your triangle, the sum of the two sides is greater than the third side. And that is in fact your triangle inequality. Okay? So these are some properties of the norms that will be relevant to us. Okay, so continuing. Let's go to orthonormal basis. Okay? So we already encountered basis, and we said that a basis is a set of vectors that span a vector space, and the set is also linearly independent. Okay? Now, we have a special kind of basis wherein we can easily compute the coefficients of a linear combination. So sabi natin dati, if you have a basis, then any vector in that vector space can be expressed as a linear combination of the vectors in the basis. But then computing for the coefficients of these vectors is not very easy. So sometimes you need to solve a linear system. Okay? But if you have an orthonormal basis, then it's just a breeze in the park. No? Masyadong madali yung paghahanap ng coefficients na ito. So this is important for us to know. So suppose that we have an inner product space. So automatically may inner product na siya. So we say that if we have a set S composed of the vectors V1 up to Vk, and S is a subset of V. Hindi siya subspace, a subset. Then we say that S is an orthogonal set if the inner product of two distinct vectors in S, Vi and Vj, is 0. Okay, so pairwise, the inner product is 0 for distinct vectors. Then we say that S is orthogonal. Kasi yung bawat vectors in S orthogonal to one another. Now, secondly is we have an orthonormal set U1 up to UK if, first of all, it is an orthogonal set. So each vector there is orthogonal with the rest. And secondly, the norm of each vector is 1. And how do you compute the norm? If you remember, it is just the square root of ui with ui. So magiging pareho yung indices natin dito, ui, and it is equal to 1. You So that implies that the inner product itself is equal to 1. Okay? So yung first condition na ito, if I is not equal to j, the inner product is 0, that is the orthogonality condition. And when I equals j, the inner product equals 1 is the normalizing condition. It is a unit vector. Now, suppose that we have a finite dimensional vector space with basis t. Then we say that T is an orthogonal basis if T is an orthogonal set, and we say that T is an orthonormal basis if it is an orthonormal set. Okay? Now the question is, do vector spaces have orthonormal bases? Okay? So for example, let's consider this. Suppose that we have a set S here. So we can verify that this is an orthogonal set of vectors. How? You just take the inner products. So ano ang inner product natin sa Rn? It's just the dot product. So you take the dot product of two vectors. Halimbawa yung first and second. Anong dot product niya? 0 plus 0 plus 0. And that is 0. Of the first and the third, that is 0 plus 0 plus 0. And of the second and the third, that is 1 plus 0 minus 1. And that is 0. So pairwise, the vectors are orthogonal. We conclude S is an orthogonal set. However, what are the magnitudes or the norms? Yung first vector, yung norm niya is just 1. Yung second, the norm niya is the square root of 2. Yung third, square root of 2 also. Not all vectors are unit vectors. So we conclude that it is not an orthonormal set. However, if we divide by the magnitude, you may get an orthonormal set. So consider this example here. So you can verify that this set T is orthogonal. And also, if you get the magnitudes, they are unit vectors. Okay, I'm using the term magnitude kasi nasa R3 tayo, and these are vectors in R3. And the magnitude coincides with the norm. So T here is an orthonormal set, and it is a basis for RQ. So take note of the following. An orthonormal set is automatically an orthogonal set. However, an orthogonal set is not necessarily an orthonormal set. So let's have some theorems. Suppose we have an inner product space. If we have an orthogonal subset of non-zero vectors, then that set is automatically linearly independent. So kapag orthogonal sila, as long as the zero vector is not there, then S is linearly independent. No? Ang sabi din natin noon, if the zero vector is there, then automatically it is linearly dependent. And we also consider that the zero vector is orthogonal to any other vector. Okay? Secondly, if S is an orthonormal basis of V, then every vector U in V can be written as U equals a linear combination of the vectors in S. Okay, sabihin mo, sir, obvious ba yun? Kasi basis siya, di ba? So, ini-span niya yung V, so U is a linear combination of these vectors. Okay. Pero how do you solve for the coefficients A1, A2, up to AN? Paano mo isa-solve yun? Gagawa ka pa ng system. Okay, gagawa ka pa ng augmented matrix. Nasa right side si U, and then i-reduce row echelon form mo pa. Wow, that can be really tedious. But if you are dealing with an orthonormal basis, the coefficients are easily computed as A sub I equals the inner product of U with the V sub I. Or in other words, the ith coefficient is the inner product of U with the ith vector in the orthonormal basis. That's really something. Kasi kunin mo lang yung dot product nila. Pag real numbers to or real vectors, kunin mo lang yung dot product. Siya na yung coefficient. Consider this example. So we already showed earlier that the set V1, V2, V3 with this as your vectors form an orthonormal basis for R cube. So consider the following vector in R cube. U equals 1, 2, 3. We want to express U as a linear combination of V1, V2, and V3. So let's just use the result here. Ano yung A1? Yung A1 is the inner product of U with V1. So that is 1 times 0 times 1 times 0 is 0. 2 times 1 is 2. 3 times 0 is 0. So you just get 2. What is the inner product of U with V sub 2? It is equal to 1. And lastly, the inner product of U with V sub 3 is equal to 3. And these are the coefficients of the vectors when you express U as a linear combination of them. So that's 2V1 plus V2 plus 3V3. So you can verify by simple addition and multiplication that this is true. So ang dali, di ba? Kapag orthonormal yung basis mo, it's very easy to find the coefficients that will make your vector a linear combination of the basic vectors. So we want to find an orthonormal basis. So how do you make an orthonormal basis? So for that, we need what is called the orthogonal projection. So we define the following. Suppose that U and V are vectors in a vector space V, where V is not the zero vector. The orthogonal projection of U on V is some vector X in the space V, where X is equal to the quotient of the inner product of U and V and the inner product of V with itself multiplied to the vector V. Okay, so tingnan po natin ano to. If this is our vector U and this is our vector V, then the orthogonal projection is like you cast a U is casting a shadow on V. Okay, so parang nag-cast siya ng shadow sa V, and that resulting shadow is the vector X. And from the head of X to the head of U, we get an orthogonal vector. So ano yung vector na ito? So if this is X and that is U, yung vector na ito is in fact U minus X. Okay, that's the vector U minus X. So take note that the vector U minus X is orthogonal to V. Okay, and also X is equal to some scalar, kasi ito, this is just a quotient, no? This is just a real number. So it's just like a real number times V or a K times V. So that means your X is either in the same direction as V, kapag positive ito. Kapag negative naman ito, X is in the opposite direction of V. In other words, X is parallel to V. Okay, and that is described in our illustration here. No? This X is parallel to V. Okay? So we will be using the orthogonal projection to construct our basis. But before that, we have this guarantee. Maganda yung before you buy something, may guarantee na binibigay sa atin. So suppose that we have an inner product space V, and let W be an m-dimensional subspace of V. Then there exists an orthonormal basis W1 up to W sub M, no? Kasi m-dimensional for W. So this is a very strong result. There exists. No? Can you easily claim the existence of something? But this theorem claims that if you have an m-dimensional subspace, of course, M here is greater than 0. then you will always find an orthonormal basis for W. And the process for getting this orthonormal basis was developed by two mathematicians, and we get the Gram-Schmidt process. So this is how we do it. First, we start with any basis for W. And we know that W will have a basis because it is a subspace. And secondly, it is m-dimensional. And that means your basis will have m vectors in it. So let these vectors be u1 up to u sub m. So to make an orthonormal basis, we must first get an orthogonal basis. So that is our first construction. So you can start with any vector in the basis for W. So let's say that V1 is equal to U1. Okay, so kahit sino doon, pwedeng U1, U2, up to UM. Okay, so let's just start with U1. Then we get the second vector. Ano nga yung orthogonal sa U1? Sabi natin kanina, ang orthogonal sa U1 is U2 minus its projection. Ito yan. No? If you look closely at this term here, you have V1 there, and then this quotient is the scalar appearing in the vector projection of U2 on V1. So this term here is the projection of U2 on V1. And earlier we said that U2 minus its projection is orthogonal to V1. So U2 minus this projection is orthogonal to V1. And that makes V2 orthogonal to V1. Okay, so now we have a pair of orthogonal vectors. And then you just continue the projection process. So here, we take the vector U3, and you get its projection on V1. And also, you get its projection on V2. And the same thing, you just subtract. And the U3 minus this equals V3 is orthogonal to both V1 and V2. Okay? And so you see that we just develop a pattern here. If we get for V4, that is equal to U4 minus projection of U4 on V1 minus projection of U4 on V2 minus projection of U4 on V3. And in general, V sub m is equal to U sub m minus the summation from I equals 1 to m minus 1 of the projection of UM on the preceding vectors V sub I. Okay? So this gives us our set of orthogonal vectors. And once you have the orthogonal basis for W, ang sabi dati, no, if you have an orthogonal set, automatically it is linearly independent. So linearly independent ito kasi wala namang zero vector dito. And also, it has m elements. And we said before that a maximal linearly independent set is also a spanning set. Okay? And it is also a basis. So this is a basis for W. So how do you make it an orthonormal basis? Well, simply you just divide each vector by its norm. And dividing each vector by its norm, we get the vector W sub I. This is the vector, the unit vector for V sub I. And combining these W sub i's gives us your orthonormal basis for W. Okay? So let's have an example. So consider this set S. You can easily show that this is linearly independent. You just form the matrix where the columns are the vectors. And you get the determinant. The determinant there is 2 minus minus 2, so that's 4, not equal to 0. So the matrix is invertible, hence the columns are linearly independent. So this is indeed a basis for R2. So let's construct an orthonormal basis. So let's start with an orthogonal basis. So let V1 be S1. By the way, ito yung diagram natin for the two vectors. S1, this is the first one, and this is the second one, S2. So our V1 is just 2, 1. Okay, so let V1 equals S1. And then for V sub 2, we get the projection of S2 on V1. So this is S2 minus its projection. And then when you simplify that, ito yung geometric na nangyayari. Take note that this is a negative number. So that's a negative 4 plus 1. That's a negative 3 over 5. So the multiplier for 2, 1 is a negative. That's why you point in the opposite direction. This is your KV V1. Ito yon. And then your V2 is just S2 minus KV1. Okay, and you get this vector here. And that is 1/5 of negative 4, 8. Now take note that we can write the vectors from any point in space. In this case, we can write it from the origin. Okay? And V2 is orthogonal now to V1. So, ano yung last step natin? We just need to get an orthonormal basis. So, we just divide the vectors V1 and V2 by their magnitudes, and this is what we get. Graphically, it's just like you draw a unit circle and yung vectors na along VI from the origin to a point on this unit circle becomes your orthonormal vector. So from here to there, ito yung unit circle natin, ito yung W1, and then ito yung W2. So that's how we draw the orthonormal basic vectors. Okay? Another example, let's say we have these vectors in R cubed. So you can verify that this is the basis for R cubed. So let's construct an orthogonal basis. So V1 is the first vector in S. The second vector is S2 minus its projection on S1 or on V1. And that is equal to this. And then the third is S3 minus its projection on V1. On V2 yung pinakita niya muna dito. S3 minus the projection on V2 minus its projection on V1. Okay, and this is the simplified form. So the set is now an orthogonal basis. So what is an orthonormal? We just divide by the magnitudes, and this is what we get. This is an orthonormal basis. Another example. Consider the Frobenius inner product. And we want to find an orthogonal basis for W equals the span of these two vectors. You can show that these two vectors are linearly independent, meaning if you get a linear combination of this and you equate that to the zero vector, the resulting coefficients will be both zeros. Okay. So suppose that we let V1 be the first vector here. So ano yung V sub 2? Yung V sub 2 is the second vector or the second matrix minus the projection of the second matrix on the first matrix. So ito yun, no? Projection of the second matrix on the first matrix. Okay, ito yung first matrix natin. And we use the symbol for the inner product. But how do you compute the inner product? It is just the Frobenius inner product, and it is just the trace of U transpose V. So U transpose, ito yun, times V. And the same for the bottom here. And you just get the product, and we are not concerned of the off-diagonal entries. We are only concerned on the diagonal entries. And this is just the trace. The trace is equal to 2, here 14. So 2 over 14. And that's what we have there. And when you simplify, you get this. So our orthogonal basis for W is equal to this set. Okay. If you are wondering what is an orthonormal basis, you need the extra step of getting the norm of each vector using the Frobenius inner product and then dividing by the norm. And I did that process, I think. And the result that I got is this. So this is an orthonormal basis now for W. Okay, so that's the Gram-Schmidt process. Now I hope you will practice doing it. Okay, so let's have some additional definitions. Suppose that we have a subspace W of V, and let V, small v, be any vector in the space V. Then we say that the vector V is orthogonal to the subspace if and only if the vector V is orthogonal to any vector in W. That is, the inner product V makes with any vector in W is 0. So to illustrate this, I hope you remember the normal vector to a plane. So let's say we have a plane there, and then this is your normal vector, and the normal vector is perpendicular to all vectors in the plane. Okay, so this vector is orthogonal to the subspace W if this is our subspace W. Okay. Now, showing that a vector V is orthogonal to a subspace W by way of showing it is orthogonal to any vector in W is impossible to implement because there are infinitely many vectors in W. So you will. Okay, so I was disconnected for a while, so let me continue. As I was saying earlier, if you are going to show that a vector V is orthogonal to a subspace W by way of getting its inner product with all vectors in W, that is a very dumb thing to do. Kasi ang dami-dami ng vectors in W. So it will take more than 1,000 lifetimes to accomplish that. But good thing is you don't really need to do that. All you have to do is get a basis for W and show that V is orthogonal to each basic vector. If it is orthogonal to each basic vector, then automatically it is orthogonal to W. Okay, because the basic vectors span the other vectors. And then we have this theorem that suppose that W is a subspace of Rn with orthonormal basis W1 to Wm, then every vector x in Rn can be written uniquely as a sum of U and V, where U is orthogonal to W and V is a vector in W. And specifically, this V as a linear combination of the orthonormal basic vectors will use the coefficients x dot w1, x dot w2, x dot wm. This is what we have used earlier for our orthonormal basis. Okay, so geometrically, just to illustrate, this is our vector x, and this is our subspace W. So x is not in W, but we can show that x is a sum of a vector in W, that is V, and another vector U, which is orthogonal to W. So this is not really unfamiliar because we have the idea that this V here is the orthogonal projection of X on W. So in fact, we define that V to be the orthogonal projection of X onto W. Okay? So let me illustrate. Suppose that we have this subspace W, a subspace of R cube, and it has the orthonormal basis. Okay, so the W here, ano yung W geometrically? Ano siya? Anong figure siya? W here is a plane. Bakit siya plane? Kasi yung dimension niya is 2 because your basis only has 2 elements. So it is a plane. So we want to express x here as sum of u and v. Now, you can verify that this x can never be a linear combination of these two vectors. Okay? But we will skip that part. So firstly, we need to find the projection of x on w, and that is our v. How do you get the projection of x on w? You showed that v is a linear combination of the basic vectors. And so you need the coefficients x dot w1 plus and x dot w2. X dot w1 is easy, no? So you just get the inner product, you get the -1 plus 4, that is a 3, plus 6, that is a 9. So you get 9 over 3 is 3. Inner product of x with the second, that is a -2 plus 2, that's 0. Minus 6, that's -6 over 3 is -2. Okay? And then you just simplify, you get the vector v there. You can then compute for the vector u. How? From x equals u plus v, we get u is equal to x minus v. So you just subtract v on both sides. And x is -1, 2, 3, and we already computed for v there. And when you get the difference, this is what we have. And this is u. Now, you can show that this u is orthogonal to w by getting the inner product of u with the basic vectors. And that is easily shown to be 0. So the inner product of this with this one is 0, and the inner product of this with this one is 0. So hence, u is orthogonal to w itself. And so, going back to our expression x is equal to u plus v, then you just have here the u. This is the v, and this is the u. Okay? Anyway, v plus u is the same as u plus v. And we were able to show that the x is a sum of a vector in w and a vector orthogonal to w. Okay, so this completes our discussion for orthonormal basis and the Gram-Schmidt process. So I hope that you learned something, especially how to construct an orthonormal basis and how to use the orthonormal basis in showing a vector is a linear combination of the orthonormal basic vectors. Okay? So with that, we close our discussion for today. Until our next lecture video.